Hello there. Welcome to Meredith Education Center, and this is Science with Master Rick. Today, we shall open our discussion on buoyancy. But first, we shall understand what pressure is and how it works. Pressure is a force. As such, it has a magnitude, or how strong it is, and a direction at which that force is directed. Now, does that mean that pressure, being a form of force, can be defined the same way we define ordinary forces? Not quite. Because knowing the magnitude of our force and the direction at which that force will be going is not enough to fully explain what pressure is. Here is an example. Let's say you are going to hammer through the wall a large nail, but instead of the pointed end going through the wall, you switch it in such a way that the head now will be used to penetrate the wall. Now, using this example, which do you think would penetrate the wall easily? The pointed side or the head? Yes, you're definitely correct. It would be easy to hammer the nail the normal way. To properly define what pressure is, we have to consider another factor to the equation, that of the area. Now, let's go back to the example of the 6-inch nail. That's why it is very easy to hammer a nail the normal way because we are concentrating all our force to only a small area. Thus, the equation pressure is equal to the amount of force per unit area. We could then say that pressure is inversely proportional to the area. Increase the area and pressure decreases, and vice versa. Let's take a look at our first sample problem, shall we? First, we are looking at a problem that is asking for the unknown force that exerted a pressure of 20 pascals. Do not forget, Pascal is a unit of pressure expressed in Newton per square meter. Second, we have to derive a new equation from the existing pressure equation in order to find the unknown force. We have two givens and one unknown. The givens are the pressure exerted, which is 20 pascals, and the area, which we set at 5.2 square meters. Third, to derive your new equation, you have to rearrange your general equation for pressure such that we will be solving in terms of the unknown pressure, which in this case is the product of the pressure to its area. Next, plug in your variables, cancel units if applicable, and do the math. Did you arrive at the same answer as mine? Good job! All right, here's another thought experiment which I created especially for you. Now, you must have known by now that I really love to perform thought experiments, correct? Okay, let's say that we have in our midst today an Indian Swami, a mystic. He claims that he can lie on a bed of nails and will never get hurt doing so. He said it is his mystical powers that prevents him from getting hurt. Is he lying or is he telling the truth? First, let's take a look at this claim with some skepticism and we'll let it pass through scientific scrutiny. We know that when force is distributed over a wide area, pressure diminishes. Lying on a bed of nails is a matter of distributed force over an area of skin. The person's weight determines the force. The total area is determined by the area of the points of the nails and the number of nails. The more nails, the more surface area, and the less weight of the person, the less force each nail exerts at a certain point. Therefore, the claim of not getting hurt while lying on a bed of nails has some truth to it after all. As to whether or not he will be comfortable lying on 100 nails or so as he goes to sleep each night, well, I'll leave it all up to you to decide, all right? Now, as to the claim of mystic powers? There's nothing mystical about it. It's purely science at work. You know that the pressure decreases as the area to which pressure is applied increases. However, for liquid pressure, pressure increases at increasing depths in a liquid. The pressure increases because the liquid at lower depths has to support all of the water above it.
Have you tried diving towards the bottom of a deep swimming pool? Or perhaps you may have noticed something heavy is inserting on your chest. Your ears would feel like it was being pushed inward. Now that's liquid pressure manifesting. As you increase the depth at which you dive, the more pressure there is. Why? Because as you go deeper, the weight of the water above you keeps piling up. Their combined weight creates that pressure. Remember, P is equal to F over A, where the force is just the thrust or the weight of the water or fluid acting on a body. For that same reason why dams are made with thicker walls at the bottom to compensate for the increase in pressure. Ordinary pressure is different from liquid pressure in terms of formula. Deriving our formula for liquid pressure, we come up with the equation. Pressure is equal to the density of the liquid multiplied by the height of the liquid column multiplied by the acceleration due to gravity. Here's a sample problem for liquid pressure. Remember, the volume of the object or body submerged is not a factor in our calculation of liquid pressure. What we want to know is how far down is the object or body submerged. Now, taking our derived formula, pressure is equal to the product of the density of the fluid, the height of the liquid column, and the acceleration due to gravity. We plugged in our given information. We know that depth is 30 meters, and the density of the liquid is for fresh water, which is 1,000 kilograms per cubic meter, and our acceleration due to gravity is at 9.8 meters per second squared. Now, in our problem, though not stated, we assume that our diver must be diving in a deep freshwater lake, basing on the density of fresh water as given. We want to know how much pressure he will have to bear at that depth. Doing the math, we come up with an answer of 294 kilopascals. Our diver will bear a pressure 3 times than what he will experience on land. If liquid pressure deals with how much force a column of liquid exerts on an object or a body at a given depth, buoyant force, however, deals with the reverse force acting on a submerged object. Now, have you tried pushing on a ball down a pool of water? Or perhaps even tried to dive towards the bottom of the pool, but, but you tried all you might and exert a lot of energy and effort before you have reached the bottom of the pool. What did you experience? Correct. You might have felt a strong force pushing the ball back up, and or felt that same strong force trying to lift you right back up to the surface, and may have even given you a hard time from reaching the bottom of the pool. Buoyancy, therefore, is a counter thrust or an upward force acting on any partially or fully submerged body or object.
We understand buoyancy or buoyant force in terms of the weight of the object submerged. Now we can rewrite our equation as buoyant force is equal to the difference of the object's actual weight and its apparent weight when submerged. Now from the sampler problem, we see in the slide, we get the buoyant force, the counter force or upthrust, acting on an object submerged or partially submerged. We know that weight can be interpreted in terms of force. Thus, weight multiplied by the acceleration due to gravity, we get force. Why? Recall, F is equal to ma, and weight is W is equal to mg. And since weight is a perpendicular force, we replace A with G. A 75 kilogram person would experience a reduction of weight of 589 newtons, or his apparent weight, when immersed in water, would have experienced a counter force of upthrust or buoyant force equivalent to 146 newtons.
The concept of buoyancy that we started to discuss in the preceding page can be explained by Archimedes' principle. You see, every object is buoyed upwards by a force equal to the weight of the fluid the object displaces. The simplicity and power of this idea is striking. If you want to know the buoyant force in an object, you only need to determine the weight of the fluid displaced by that object. Archimedes of Syracuse discovered this concept 2,000 years ago. He postulated that the force buoying an object immersed in a fluid is equal to the volume or weight of the fluid it displaced. Why is there truth to this statement? Why is this even more true to this day than during his day? Well, the answer is pretty simple. Do you still remember your properties of matter? The property of impermeability of matter? It states that no two units of matter can occupy the same space at the same time. Now, something has to give way, and in this case, fluid or liquid in a state in which its molecules are not tightly packed and conforms to shape changes of its container will have to give way to the occupied space in terms of the volume of the immersed object. Now, with our more pronounced understanding of the physical laws, principles and laws that have been discovered, theorized, and postulated centuries ago couldn't have been closer to the truth, as our advanced understanding and knowledge of the physical sciences could easily either verify these as truths or debunk these as false ideas. We can write the equation for buoyancy as the product of the volume of the displaced liquid, the density of the fluid it is immersed in, and the acceleration due to gravity, which really is the Archimedes principle all along.
Here's a sample problem on the application of the Archimedes principle. Suppose an object with a volume of 0.346 cubic meters, or roughly about the size of, say, about 115 SUV engines. That would be 115 four-cylinder diesel engines with a displacement of 3,000 cc's each, kind of like the engine of your Isuzu MU7 or Isuzu D-Max pickup truck, dumped together and then thrown into the ocean. That's how large 0.346 cubic meters or 346,000 cubic centimeters is. Now, doing the math, we found out that the counterforce that pushes it up is about 3,472.2 newtons, or equivalent to about 354 kilograms of force pushing it back. And that ends our topic on liquid pressure and buoyancy. And until next time, remember, science is cool.